In the heart of Tokyo, a towering giant stands tall, defying the laws of physics and engineering. This is Japan's first Supertall Skyscraper, an awe-inspiring feat of human ingenuity that's taken the world by storm. But with earthquakes being a constant threat in Japan, the question on everyone's mind is whether this towering structure can withstand the forces of nature. In this video, we'll take you on a journey into the heart of Tokyo's skyline, exploring the insane engineering behind this marvel of modern architecture and revealing the innovative techniques that have been employed to make it earthquake-proof. The most populous city in the world, Tokyo, is home to over 37 million people and has acclaimed restaurants and stunning temples. It is now adding a super tall, earthquake-resistant tower to its list of landmarks. The main tower, which has the intriguing moniker of being 330 meters tall, will be the city's highest skyscraper ever built. Although earthquake-resistant structures are nothing new, Tokyo is one of the most difficult cities to construct them in. Here, disaster-proofing the infrastructure is a matter of life and death. It becomes more difficult to ensure the safety of Tokyo's higher structures. The recent catastrophes in Turkey and Syria serve as a horrifying reminder of the havoc that building collapses may cause. So, what precisely goes into creating the highest tower in a city that often experiences earthquakes? What distinguishes this recent advancement from others? You need a little background information before we go on to this amazing edifice. While earthquakes are one of Japan's most frequent natural disasters, the country is also recognized for its cuisine and bullet trains. In actuality, hundreds of tiny earthquakes are noted annually. Although the majority go unreported, the nation is located in one of the most seismically active regions on the globe. The so-called Pacific Ring of Fire runs directly through Tokyo. The Ring of Fire, as it is known in science, is a region where many of the Earth's continental and oceanic plates collide. In very basic terms, an earthquake or volcanic activity happens when the plates meet, abruptly shatter, or get shifted along these lines. 2011 had one of the most powerful earthquakes to hit Japan. The area was shaken by the magnitude 9 catastrophe, which was followed by a tsunami. Both incidents resulted in the destruction of a nuclear plant, as well as thousands of structures nationwide. Tokyo's structures are all designed to resist earthquakes as best they can, given the city's high level of activity. Estimating the amount of motion is critical. We design to acceleration rather than a certain magnitude, according to Ziggy Lepkowski, Assistant Director of Seismic Design at Arup. The lateral load of the building is determined by the mass of the structure and the acceleration of the earthquake, and that's a skewed perspective on how we determine the load to apply to the structure. To do our estimates, we look at the amount of acceleration we may expect from the biggest earthquakes in the area. Building regulations and technology have been enhanced considerably further since 2011. Due to the city's lengthy history and most current regulations, few tall buildings have been constructed, and none exceeding 300 meters in height are considered super talls. Now, we're just referring to legitimate skyscrapers here. We're not talking about structures like the Skytree, which is much taller but isn't considered a building. Tokyo's highest structure at the moment soars 255 meters above the city. But that's about to change, because the main tower, which just topped out, will be heading your way in 2023. The structure has an open floor layout inside and 4 carving glass petals around its roof. Along with the east and west towers, it will be located in the Toranomon Azabudai project, also known as the Azabudai Hills, a brand new urban development. The 8.1 hectare neighborhood has a lot of green space as well as stores, offices, and homes. To maintain sustainability, all of the power provided will come from renewable sources. The project's overall goal is to build a kind of city inside a metropolis. More crucially, the 3 main buildings will be earthquake-proof and capable of housing up to 3,600 people in case of a catastrophic natural catastrophe, even if an earthquake, as powerful as the one in 2011 occurs. But it won't only serve as a temporary refuge. The development is planned such that operations and daily living can continue even if other regions are damaged. Even if it takes a certain sort of line manager to urge you to continue working during an earthquake, you get the picture. Most engineers probably wouldn't feel comfortable developing a place with this objective in mind. The stakes increase in height as the building grows. A tall building, it needs a vertical system that can support the building's weight in gravity. And then, it needs a secondary system that can handle lateral loads and buildings everywhere. Lepkowski added, whether or not an earthquake zone, it must take into account wind loading. We also have a lateral load if we are in an earthquake zone, but it's a cyclical load. It thus has a backward and forward motion. Therefore, we must make sure that we never find ourselves in a scenario where it will fail. that we can maintain the vertical system, and that we can protect the structure from collapsing. But Japan is adept at rising to the occasion. High-strength steel and concrete will be utilized throughout the whole of the towers, coupled with well-placed vibration control mechanisms that lessen shaking. The active mass damper, a weighted device that rests towards the top of the structure and helps prevent swaying caused by strong winds or shocks, is one of them. But it takes more than one enormous damper to make a Supertall disaster-proof. Various minor parts are also distributed thoughtfully about the structure. This is how they'll operate. First up are mechanical oil dampers, which function by exploiting the substance's fluid resistance to absorb shocks. Also available are viscous wall dampers. These use a high viscosity material's resistance, or more simply put, how much a liquid or gas can resist changes in form, to absorb any movement. Unbonded braze dampers, which are flexible steel pieces that can absorb part of the energy from an earthquake, are the last option. Now, engineers must take other factors into account in addition to vibration reduction. Although taking these precautions during a seismic event can save lives, the aftermath is also important. The Toranomon Azubudai project has developed a method to keep it functioning, since calamities often cut off electricity. The main tower's basement will see a cogeneration system built. The tower will be able to deliver energy to the whole complex for up to 72 hours, since it will be immune to any kind of disturbance. This would imply that inhabitants' everyday life will go mostly undisturbed. And that's crucial, since this whole project has been carefully planned to accommodate its users. Planning an architectural project began with a diagram showing the movement of people around a central plaza. Building locations were a secondary consideration. The Toranomon Azubudai project was also possible to maximize green space and design demands to be positioned within walking distances by constructing higher and more compact towers. Its objective is to provide areas where locals may readily interact with one another. Compact communities like this outside of Tokyo have been utilized in Japan's past attempts at economic revitalization. Toyama advanced this idea by modernizing public transportation, enlivening its downtown, and making the city more walkable. Toranomon Azubudai's creators assert that their goal is to build a location that people may run to rather than from. And if their main tower succeeds, maybe the rest of the nation will continue to construct higher structures in the years to come. The recent tragic occurrences in Turkey and Syria serve as a stark reminder of how much trust we put in the engineers and construction crews that work every day to build our built environment. It's crucial that we fully analyze all instances when anything goes wrong, gather the data, and draw conclusions to prepare for the new developments. We hope you enjoyed learning about the innovative techniques used to make this towering structure earthquake-proof. Now, it's your turn to join the conversation. We want to hear your thoughts and opinions about the incredible engineering behind this landmark building. Do you think it can withstand Japan's earthquakes? What other challenges do you think architects and engineers face when designing Supertall skyscrapers? Leave a comment below and let us know what you think. And don't forget to hit the subscribe button and turn on notifications, so you can be the first to know when we upload our next video on the latest advancements in engineering, technology, and innovation. Thanks for watching, and we'll see you in the next one.